Did anyone watch the videos? I did not check the YouTube counts beforehand.
I tried on Monday.
Oh, really? I would be proud? Wow. Well, because I went home and recorded all those videos, so I hope you guys at least took the time to watch them. Anyway, okay, so we're going to continue on. Any questions from that material? We're talking about multiple comparisons, traps, and talking about p-value. Did covering the p-value exercises make any more sense for you guys when actually looking at the data? How to use the p-values to really tell you whether or not you can take actual statistical significance from something, and then also looking at the clinical implications of that. Right, so not all things that meet their p-value does not mean that it's going to be clinically significant or even all that interesting, right? Okay, so we'll continue on. Today we're going to be talking more about statistical tests. So how do we generate those p-values? We're going to talk about some of the tests that are used to do that. So we're going to be looking at how we can compare things that have observed versus expected frequency. So this is where our chi-square test is going to come into place. This is a good way to look at frequencies of things that are occurring and whether or not that is statistically significantly different than what would be expected to occur just by random chance. We'll talk about that. We'll look at how we can compare proportions to one another with different groups, so that way we can use things like t-tests and generate things like relative risk, odds ratios, numbers needed to treat, all those things you probably heard about before. We'll look at how you actually get those numbers. And then also look at things like case control studies where we're going to see more of the odds ratios pop up there. We'll define what an unpaired t-test and then how that compares to things like paired t-tests or single sample t-tests. We'll learn about some of the assumptions that go into those types of tests when we run those. And then we'll talk about things like correlation coefficients and causation, and then we'll actually go even into more detail on that when we get to the next section. So first thing we're going to look at is comparing the observed and expected distributions that occur. So sometimes you want to look at the occurrence of a particular event or a particular situation that's happening, and you want to find out whether or not that's going to be following an expected distribution. So say, for instance, I was looking at in the case of male versus female admissions into PA schools, and I were to compare kind of the national average versus you guys, we could do and look at the actual observed frequencies of male versus female and compare that to see, to the actual the expected frequencies and see if that's statistically significantly different. Again, it doesn't tell you necessarily there's any causation between that. You can just tell that there is a difference there that is not just due to random chance. So that's one example. Here's another one where they were actually looking at heart disease and why it's the most frequent cause of on-duty death amongst firefighters. And so they wanted to see if there was anything that were determining where the deaths were occurring, and why that more of these deaths were actually occurring when they were fighting fires, and were those were those values different than what would be expected just due to random chance. And so in this case, the null hypothesis when looking at this would be that deaths amongst firefighters would occur randomly throughout their time, on their shifts versus during a very specific period of time. And as you might imagine, just due to common sense, you would automatically think they'd probably be dying more frequently during the most dangerous times of their shift, right? But we can look at that and see if there's any true difference there or not. So again, we're going to use this data to see what the expected frequencies of deaths occurring based on the time that they're spending during their shifts versus what was actually happening. So basically the way you can look at this is, one, you can see the different categories here. So you can see the duties that the firefighters were performing, right? So you can see the fire suppression, the actual firefighting part of it, physical training, other duties. And you can see the percentage of time they actually spent doing all of those in the far right category, right? So based on that, if I were to have a total of 449 deaths that had occurred, 2% of that would end up being 9 deaths, right? So if deaths were just occurring randomly during this time period, you expect about 2% of them to occur during that time period, versus they spend the bulk of their time doing other duties. You expect the majority of deaths to occur during that time period, right? That would make sense. That would be the expected frequencies. And then when you actually look at the true numbers, you see that those are very different from what the expected frequencies are, right? So now we can run statistical tests to see whether that could be due to random chance alone, or whether that is going to be variant enough or far enough away from those expected frequencies that it's unlikely to be due to chance alone and is statistically significantly different. So the way we can do that is with our chi-square test, or goodness of fit test. So again, looking at this, we can see that the discrepancies seem pretty large between what was observed and what was expected. And using that chi-square test, we can compare those and end up getting a chi-square value that will end up informing our p-value. And if that p is, usually the alpha is set at 0.05, if it's less than that, then you would consider it to be statistically significantly different. So the way you normally will kind of organize this data is usually into these tables. So this would be considered like a chi-square table, where essentially you would have your different categories, and then you have your observed versus your expected, and then you have these totals categories. And so based on that, you can basically do the math and find out the differences between your observed and expected, and that will eventually get you to a chi-square value. So again, basically we're just combining the discrepancies between the observed and the expected counts to calculate a p-value that will tell us whether or not the null hypothesis was true. So again, if our p-value was, say, greater than that threshold of 0.05, we would say that there is, the differences that we're observing between the expected and the actual observed frequencies were just due to chance alone, versus if we can reject the null hypothesis, that p-value is low enough that there is a statistically significant difference there, right? So there's something about how they're spending their time or what they're doing during that time period that leads to more deaths during those periods, which again, common sense would lead you to think, yeah, that makes sense. If you're fighting fires, that's pretty dangerous, right? So again, p-values are large. The observed distribution does not deviate enough, and so you would say that would not be statistically significant. We'll look at some more examples of where you can use these as well a little bit later on. Again, I'm not going to force you to do the math on any of these, but just so you can tell where these values are coming from, this chi-square value that we're coming up with is basically going to be the sum of all these differences of the observed minus your expected squared over the expected. And so I'll show you the table a little bit later. It kind of shows you how you do that math to get those frequencies. But essentially, using that chi-square value and then determining how many numbers of degrees of freedom that we have. And again, in this case, normally degrees of freedom were calculated as being your n minus 1. Here in chi-square, it's usually going to be the number of categories you have minus 1. Right, so if we had, say, 4 different activities that the firefighters were doing, your degrees of freedom would end up being 3, because you just take your categories minus 1. And again, most of the time it's going to be computers doing all this for you, so you don't have to calculate this by hand, fortunately. So again, just another way of looking at it, looking at our observed values, you can see that another way you could potentially do this is if you were looking at disease or exposure versus disease outcomes, right? So if you had patients who were exposed to a certain, say, environment or exposed to some sort of chemical or anything, what it happens to be, and whether or not they manifest the disease, this is another way you can start to categorize this data, where you can look at the observed frequencies, and then using those totals, you can end up calculating what your expected frequencies are, and then again derive a chi-square value from that. The way you actually calculate those expected frequencies, if you were to just have the table that we had before, and again, this looks confusing, but essentially all you're doing is multiplying your totals columns and then dividing it by the absolute total, right? So you take in the category of people with exposure that had the disease. To get that expected frequency, you would just take your totals of A plus C times A plus B, and then divide that whole thing by the entire total number of exposures, or entire total number of observations you had, right? So again, just realize that there's ways to generate those expected frequencies, and then you can compare that to the observed and come up with a p-value that kind of tells you whether or not your observed is going to be statistically significantly different from what your expected frequency would be. That make sense? Okay. Shaking your head no? Not making any sense?
I'll figure it out later.
You'll figure it out later, okay. But again, this is just really good to look to see if you're looking at an exposure to something, if you're looking at some sort of risk factor for a disease, and then the actual, whether or not the patient's manifested that particular condition. It's good to look to see, like, okay, is there something else going on here, or is this just due to random chance that this risk factor seemed to be associated with these diseases, right? Kind of gives you an idea of looking at that. So I guess for an example, so when I was doing my research, remember I was talking about we were doing the coral snake antivenom shortage and looking at patients who did or did not receive coral snake antivenom, if they did any worse. So an example for that would be if I was going to do a chi-square test, and we did a number of these, where we would say patients who got the coral snake antivenom and patients who did not get coral snake antivenom, and then compared whether or not they were intubated or not. right? So I can compare those frequencies, use those categories to see my observed frequencies, and then figure out these expected, and then determine whether or not the chi-square value was significant enough to have a low p-value. So again, you can do any kind of number of situations like that where you're basically categorizing things and then calculating those expected frequencies.
What do you end up figuring out?
So we ended up figuring out, you can actually go read the article if you like. No one wants to do that, I'm just kidding. Basically what we were actually looking at was seeing, back in the day when patients were bitten by coral snakes, almost everyone got the antivenom right off the bat. And so nowadays, since we had more of a shortage, we were kind of waiting to treat patients for longer until they actually manifested symptoms. And so our hypothesis going in was that, well, just because we're waiting to treat them until they have symptoms, they shouldn't be doing any worse. And in fact, we're actually going to limit how many patients are going to have an anaphylactic reaction, because the antivenom is a pure horse protein, so it's very, very immunogenic. And so we actually ended up finding there were no real differences between the groups. That patients who we waited to give coral snake antivenom to didn't appear to do any worse. So that's essentially what the findings ended up being in general. Okay, so that was chi-square goodness of fit test. The next thing we can look at is comparing proportions, and so we'll look at this in the context of prospective and experimental studies. Prospective means what? Yeah, so things that are happening in the future. I'm starting a study now that I'm looking at data that's happening in real time, right? What would be the converse to that? Yeah, retrospective, right? So to get a little bit of the lingo down, so the next two sections are going to be looking at the question, does an exposure to a risk factor cause disease or not? So that's kind of a general question we're going to be looking at. So we'll talk about incidence and prevalence more when we get to the epi section, but essentially incidence is going to be the rate of new disease or new cases of disease popping up, and then prevalence would be a fraction of a group that has the disease. So prevalence is usually done as kind of a snapshot. So where if I were to take a snapshot of you guys right now, like who has hypertension, that would be the prevalence of it, versus if I were looking at in real time to see what the incidence of new rates or new cases of hypertension would be as we go forward, especially as the number of tests you're taking continue to increase. I'm sure the blood pressure continues to rise, right? Probably not funny. Okay, a little too close for comfort. The other thing you can do is a cross-sectional study where basically you're taking a single sample of subjects that are selected without regard for whether they have the disease or if they've been exposed to the risk factor, and then based on that, based on the group of patients that you get, you would divide them up into groups based on their previous exposure to the risk factors. That's where you can kind of come up with those contingency tables we were mentioning before. And then based on that, you would look at the prevalence of disease being compared between the two groups, right? So I could take a whole sample of you guys as a snapshot right now, break you up into different groups as risk factors, and then look to see the prevalence of disease at that time period to determine whether or not there's some difference there. So we mentioned prospective studies. The most frequently that you'll see are going to be two groups of subjects that are selected, usually one with an exposure and one without, and then you're going to be observing over time to determine the incidence rates for the two groups, right? So you're not really looking for prevalence, because prevalence is more done as kind of a single time period, versus incidence will be the new occurrence of your outcome. And then an experimental study just really means that we're doing a single sample of subjects that are randomly selected and divided into two groups randomly as well, and then each group would end up getting a different treatment or no treatment, right? So you can have placebo or no treatment whatsoever, and then your outcomes or incidence will be observed again in real time as you go forward. Then you can also have what we call case control studies, and so these are going to be two groups of subjects that are typically selected. Again, you'll find studies where they'll use more groups, but let's just keep it simple for now and just say for these case control studies we're dealing with two groups. And that you'll say, okay, out of you as a group of patients, these guys have the disease state or the condition, so those would be the cases, and then I end up matching them up with patients who do not have the disease and try to get them to be as similar as possible. So again, I would be matching patients who are similar in age, similar in gender, similar in risk factors to compare them to. And so in general, for a lot of case control studies, you're going to see that you'll have, for every one patient with the disease state, you're going to have 2 or 3 patients or even more potentially cases that work as a control, right? So that way you don't have to worry about things like confounders, which can skew your data. We'll talk more about confounders later. So, and then basically by looking at those patients, going back in a retrospective manner, you can look to see what kind of possible risk factors might have been influencing how your cases got the disease in the first place. So an example, here's a clinical trial here in 1993. So this is, again, kind of early on in our understanding of treating HIV. But essentially what we're doing is studying the effectiveness of zidovudine, which is a antiretroviral drug, shortened to AZT. So if you ever see AZT, that stands for zidovudine. And again, it goes back to the chemical name they're shortening there. And essentially they're treating asymptomatic patients with HIV with normal CD4 counts. Right, so these are asymptomatic patients that have the virus, but they still have a normal CD4 count. So they're not very well progressed in their disease state yet. So we know that AZT had proven effectiveness in patients with AIDS that were asymptomatic with HIV in low CD4 cell counts. So the thing they wanted to look at here is to see if by giving these patients who had regular counts of CD4, if you could prevent disease progression by giving zidovudine, right? So the final question was, does treatment with AZT reduce the progression of the disease? Okay, so this is a randomized trial, meaning that you took patients who were sampled from a population, and you randomly assigned them. And again, this is going to be a double-blind prospective study, meaning that double-blinding means what?
Researchers don't know.
Yeah, so the providers who are giving the drug don't know who's getting what, and then the patients don't know what they're getting, right? So they could either be getting placebo or zidovudine. And nowadays, we know that we can never do a study like this. Anyone know why? Right, because now we know that the drug is really effective for that, so you really wouldn't want to withhold treatment. So if you wanted to do a study similar to this nowadays, you would be using kind of gold standard therapy versus, say, whatever your experimental group would be, right, to see how disease progression would go. But this is back in the day where you could still do this because we didn't have an idea of whether or not even giving this drug to these patients who were asymptomatic and had good CD4 accounts, what it would even do for them, right? So this is still kind of early on in trying to figure all this stuff out. So again, it's double blind. Really only the researchers are going to have access to who receive what kind of treatment, and they're usually being randomized. They usually have a number associated with them that the researchers have kind of a book they can match it up with. Yes, prospective, so we're going to be looking at 3 years of data to see which of these patients end up progressing in their disease state. So looking at this, you can see that patients that got the AZT, they ended up having 76 of those patients had disease progression versus 399 who had no progression. And again, that was defined in the article, so it would be either probably a certain drop in CD4 cell count or some sort of AIDS equivalent disease state like PCP pneumonia or Kaposi sarcoma, something like that, I'm sure. And then you have your total number there, and then you'd have your placebo group being compared to that, and then you have your totals there as well. So now the goal is to match these proportions and look at the risk and the change in risk that occurs either by giving AZT or not. So looking at the disease progression in the patients receiving AZT, we saw that 16% of them had progression. So that was calculated by just dividing 76 divided by 475, right? So their risk of having disease progression was 16% in that group. And that confidence interval ranged anywhere between 13 and 20. And then for the placebo group, we saw that 28% of them had disease progression. Again, that was just 129 divided by 461. Now notice that the sample numbers are not exactly the same. And is that a problem? Not generally, right? Because in a perfect world, you would have completely even groups, but as long as the numbers are somewhat close to one another, you're generally pretty good to go, right? If you're looking at a case control study, that's where you're going to see a lot of disparities between numbers because your cases are going to be far fewer because you're going to have 2 or 3 or 4 controls for every case that you have in those types of studies. So that's where you might see some big discrepancies in the numbers there. But here, as long as they're close, that's generally a pretty good thing for us. So, and then looking at the confidence intervals for the placebo group, it ranged anywhere between 24 and 32%. Okay, so that's kind of our baseline results we have just from that information. Now we can start to compare these and see what kind of actual reduction in risk we have by giving AZT. So, looking at this, we can look at what we consider to be actual attributable risk. And so this would be an absolute risk reduction. So if you ever see absolute risk reduction, this is just going to be the risk in one group subtracted by the risk in your control group or your experimental group. So in this case, the absolute risk reduction was 12%, and that's easy to calculate because it's 28 minus 16%, right? It's pretty easy. And then looking at that, we see that the 95% confidence interval for the difference ranges between 6.7 and 17.3%. Now here, what number would this percentage have to cross in order to be considered non-significant? Think 1? Or would it be 0? right? So that confidence, remember, it's going to be ranging there. And for when we're doing differences in means, so if we're subtracting or adding means, something like that, 0 is going to be your point for significance, right? Because again, if there was no difference between these groups, if we would say that the null hypothesis is true and the AZT does not influence the risk for disease progression, that difference there would be 0, right? Because the risk would be the same between both groups. Okay, so if my confidence interval encapsulated 0, then I would know that that would be a non-significant result. So that's with absolute risk reduction. We're going to look at risk ratios, and we're going to see that when you're doing a ratio or a proportion of means together, that's where 1 is going to be your point for non-significance. Okay, so I'll show you that in just a minute. And again, here the p-value kind of demonstrates that it's less than 0.001, so it's a very small p-value, so it's very, very unlikely that this change in risk is going to be due to just chance alone, right? So I can safely reject the null hypothesis and say that it appears that AZT reduces the risk of disease progression in these patients with HIV who are asymptomatic and have good CD4 cell counts, right? So, and again, looking at that confidence interval, you can know that the true value, you're 95% sure that it ranges anywhere between 6.7% reduction or all the way up to a 17.3% reduction. Somewhere in there, but it is going to be an actual reduction. Okay? Everyone with me so far? Okay. So then if we assume the subjects represent the larger population, and again, assuming that we randomly sampled these patients, we can assume they're normally distributed. We can generalize this information back out to these patients. We would be 95% confident that AZT treatment will reduce progression of disease anywhere between 6.7 and 17.3%. Kind of what we already said. So how could we look at the number needed to treat? So have you guys heard that term before? Okay, so the number needed to treat is basically how many patients you would have to see who have asymptomatic HIV with high CD4 cell counts, how many patients you'd have to give AZT to in order to get to have one patient not have a progression of disease, okay? And so essentially what we can do is look at the absolute risk reduction and take the reciprocal of that. So just do 1 divided by the reciprocal, and you get a value here because we said it was a 12% reduction, right? Because it was the 28 minus 16. We had 12% reduction. If you flip that over, 1 divided by 0.12, you end up getting 8.3. So essentially what that means, for every 8 patients that I give AZT to that fits in this population, I should have 1 patient who does not have a disease progression. Okay?
That sounds awful.
Sounds awful?
Right, like so 7 people are not going to get any benefit from this.
So those 7 people might not have had any disease progression to begin with in the first place, right? So because again, not every single patient during that 3-year period had disease progression. You saw a significant number of them did not, right? So you're just saying that for those patients, I'd have to treat 8 of them to at least have 1 to prevent 1 disease progression. Okay, so it's a good thing because you're preventing disease from occurring, right, or from progressing at least. But you can start to compare interventions now to look at things like, okay, well this intervention, has a number needed to treat of 2, versus this one has a number needed to treat of 8. So which one would be a better? Which one do I get more bang for my buck? Yeah, because I want to be able to treat fewer patients to have benefit from. Okay, so it's important when you're comparing different therapies, and then you can also start to look at some of the financial impacts of that as well. So again, if I have a patient, or if I have a treatment that, my number needed to treat is 8, but costs pennies, versus one that's, number needed to treat of 2, but it costs, 100 times as much. And then you start getting kind of some gray areas as far as which one is actually going to give me more bang for my buck. You have to kind of take a more kind of utilitarian kind of view on that sort of thing to look to see, what's going to be the better treatment, right? So we won't get too much in that in this course, but just realize that number needed to treat is a common thing that they will use to kind of compare therapies to see, which one is, going to be more bang for your buck, essentially.
But you don't know which one is not progressing naturally and which one is actually being prevented by the drug AZT.
Mm-hmm. Yeah, exactly. Yep, so you're just knowing that if I treat 8 patients, I should have 1 patient that does not have disease progression. Again, this is all probability. That's why none of this is going to be set in stone concrete. You could have another study that comes out and says, no, it's more like 24 patients. And then it's like, okay, well now you're calling into question how effective your therapy really is, right? So that's why reproducibility of studies is so important in order to confirm these results, okay? Anywho, so again, looking at the confidence interval for that that number needed to treat, it could range anywhere between, say, like 6 patients all the way up to 15 patients. So again, it could be somewhat of a range there. And if I were to have a study that had a larger patient population, what would that do to my confidence interval? Yeah, it should narrow it down, right? So I should have a better idea of what that true number needed to treat is if I were to have a larger sample size. But again, sometimes you're really limited based on the type of study you're doing, your funding, things like that. So anyway, and then we mentioned also that a number needed to treat, a lower value is going to be preferred. Okay. There's also the concept of a number needed to harm. So if you were to have something, say, that cause an increased risk of, say, disease progression, whatever it happens to be, that number, you'd have an absolute risk increase, you could get the reciprocal of that and get a number needed to harm. So you'd say, okay, so if I give this treatment to so many patients, I could have, if I treated 24 of them, they would have this outcome. So very frequently you'll see something like a number needed to treat for, so say for instance I was giving a new statin to patients with cardiovascular disease, and so my number needed to treat was, say, 10 to prevent coronary death, but then my number needed to harm for an adverse effect, something like rhabdomyolysis, was, say, 100. So I knew that for every 100 patients I were to give that drug to, I could have one case of rhabdomyolysis. So sometimes you'll see numbers need to treat, numbers need to harm used in the same study to kind of talk about different aspects of it. You had a question?
Can you use this kind of stuff in malpractice lawsuits, or is it usually not brought up?
Not necessarily in malpractice lawsuits, because generally, you're going to be more looking at kind of like guidelines. You're going to be looking at current best practices and things. So a lot of this information kind of gets incorporated into big meta-analyses. They get incorporated into guidelines and things like that to find kind of what the best practice should be. So typically you're not going to say necessarily like, well, you treated 8 patients and my patient had a disease progression. What's up with that? I don't think that would ever really come up, but you never know. All sorts of stuff can come up in a court of law. You have a question?
Yeah, for the confidence interval here,
Mm-hmm.
how did they get this measure?
Oh, that's a good question. So they just took the absolute risk reduction that occurred there that had that 95% confidence interval. You just did the reciprocals of those. You get those values. Yep. Good question, though. Okay.
I don't understand.
So if you go back to the last slide. So we're going to go back to the last slide. So I know my absolute risk reduction here was 0.12, right? So 12%, right? And there was a confidence interval on the previous slide that was associated with that. So you see that range there? So if I just take the reciprocal of those numbers, that's where you get this 95% confidence interval. Okay. And again, if you're looking at number needed to harm, would you want a larger number or a smaller number? Larger number, right? Because you want to have a lower chance of causing harm for your patients, whatever it happens to be. Okay. Yes.
So if you have you need 100 people to harm. Does that mean 1% of your people get harmed?
That the probability is that one person out of that 100 would have whatever outcome it was. So it could be headache, it could be death, it could be whatever happens to be, whatever event you're looking at. If it's a negative one, you'd say that's a number needed to harm.
Okay. So what could I say? 1% of my.
If it happened to be 100, then you could say 1% of patients who receive this would, Yep. Okay, again, when we're comparing relative risk, this is going to be when we're doing the ratio between two proportions, right? So this is where one's going to be our point of significance here. And so we can compare by looking at the progression in the treatment group divided by the progression in the placebo group, okay? So this would be that 6% divided by 28%, and then I end up getting a relative risk of 0.57. So what does that number mean, that 0.57? Essentially what it means is that patients who were treated with AZT were about half, or I guess maybe 6 out of 10 or 57% as likely as placebo to have disease progression. Okay, so it basically says your patients who are receiving placebo, they're at this baseline risk of 28%, and patients who are getting AZT have about half the risk of that, of having disease progression. So again, it's a way to compare the proportion of your risk that's occurring in each of those groups. And so when you're doing this, relative risks are always going to range between 0 and 1. So that means that so again, if it goes between 0 to 1, then you know that your relative risk is lower for whatever your outcome is, versus if I have one that's going to be greater than 1, then I know my risk is going to be higher. Right? So if I were to compare these two groups together and say I were to have a higher risk of disease progression in the AZT group, that value would end up being greater than 1. Okay, because that risk would end up being above the baseline. And so here, again, if we're crossing 1, if the 95% confidence interval encapsulate 1, then we know that the results are not significant. And here you see the 95% confidence interval range between 0.44 and 0.74. right? So the true value resides somewhere within there, we're 95% sure, and does not cross 1, so we know that would be a significant result.
You're talking about the relative risk when you're saying it's greater than 1, right? Not the confidence interval.
Confidence would be greater than 0, right?
So the relative risk, if it's between 0 and 1, that means that the risk of whatever event you're looking at is lessened in your experimental group. If it's greater than 1, then it's increased risk. But if it encapsulates 1, that 95% confidence interval, if it includes 1 anywhere near that, then that means it's not going to be significant, right? So because your control group is always going to have your baseline risk of 1, whatever it happens to be, right? So you're comparing the proportion of risk there between your experimental group and your control group. And so if I'm less likely to have disease progression in that experimental group, I'm going to be less than 1, right? Because it's going to be a certain percentage of that. Versus if I were to say, my disease progression risk was twice that of, my control group, my relative risk would end up being 2, right? But again, if it encapsulates 1, the 95% confidence interval, it means it's going to be non-significant. We'll look at some more examples of that in just a little bit. Okay. So again, when calculating p-value, all p-values start with the null hypothesis, and in this case, it would be the AZT does not alter the probability of disease progression, right? So then, this can help us to answer the following question: that if the null hypothesis is true, what is the chance that the random sampling of subjects would result in the incidence rates as different or more so than what was observed, right? So what are the chances are that we would get a result this extreme or more so when just random sampling patients from this population, okay? So in this case, when we're comparing the relative risk between the control and the experimental group, we end up seeing the p-value is less than 0.0001. So again, the chance of this occurring by random chance alone is very, very small. We can say that this group is statistically significantly different in those patients receiving AZT than ones that did not. Okay, so very, very small chance that the null hypothesis would be true. Very unlikely we're making a type 1 error based on the data that we're looking at. And again, type 1 error is what?
Falsely rejecting.
Yeah, so falsely rejecting the null hypothesis or making a false positive result, right? Okay, so then we can also look at comparing proportions in case control studies, but this one's going to be a little bit different where we're looking at odds ratios versus relative risk. Because again, when we're doing case control studies, we're more dealing with prevalence of disease rather than with incidence, right? Because when we were looking at the AZT example, we were doing a prospective study where we could see new incidence of an event versus when we're doing a retrospective case control study, the patients have already had their outcomes, we're going to be looking more at prevalence there. And so this is where odds ratios are going to come into play. So this is an example of a study where they're looking at whether or not the cholera vaccine worked, right? So here it's a case control or a retrospective study where they're comparing people who developed cholera and they were seeing whether or not they were vaccinated, okay? So the exposure would be whether or not they were vaccinated and then the result would be whether or not they actually got the disease state. So in this case, what would be your independent variable? Let me think. Because then how you're dividing up your patients. Yeah, so those with the exposure, so those that got the vaccine or not, and then you look at their disease prevalence, right? So in that case, the independent variable is going to be the thing that we're controlling, we're setting, and it'll be whether or not they got the cholera vaccine, right? And then the dependent variable is going to be whether or not they actually had the disease state, right? So go back and remember that you should be able to identify what is going to be the dependent versus independent variables in these studies. Okay, so again, you're looking at one of these tables where you can see whether or not patients received vaccine or got no vaccine, and then we saw the cases of choleras and cases of cholera actually occurring. And notice here that your total number of patients in the cholera group is 43 versus 172 in the control group. So is that a problem in this case? In this case, it's not, because remember we're doing a case control study, so very frequently, in order to control for a lot of confounders like changes in age, changes in disease severity, whatever happens, different confounders that could influence our data. For case control studies, we typically have several patients for every one case patient, right? Several control patients for every case patient we have there. So that disparity in numbers is okay. That's expected in case control studies. Exactly right, because if you imagine like what's more likely to occur, someone to get cholera or not. Probably unlikely for them to actually have a case of cholera, right? So you definitely have fewer numbers of patients who are actually manifesting the disease in that case. That's why the numbers are much fewer. Okay, so in this case, because we're not looking really at incidence, we're more looking at prevalence, you don't really want to calculate a relative risk from case control studies. It's really not going to be a valid way to analyze the data there. What we can do, and again, looking here, the cases and controls are not going to be even, because again, when we don't have the entire population's data, because again, it's going to be impossible to actually capture all of that data. So we're going to use those case controls to help kind of simulate that a little bit to have a better comparison there. And then the incidence can't really be calculated, right? Because we're doing just prevalence at that point. So any relative risk calculation is going to be invalid. The thing we're going to do instead is going to be looking at our odds ratios. So again, odds ratios are going to be the best thing for these case control studies. And so essentially, when you're looking at relative risk, you're looking at probability of something occurring, versus with odds, you're looking at basically the odds of something happening. And I'll give you an example of how those differ a little bit there. So again, the probability that an event will occur in the fraction of times you expect to see that event in many trials. Again, that can range anywhere between 0 to 1, right? And then the odds are going to be defined by the probability that an event will occur divided by the probability that the event will not occur. And that can be any kind of positive value, or it could be 0. So it can range anywhere between 0 to any positive integer. I'll show you an example of that in a second, because I know those definitions are not real great. If you need to convert probability to odds, you can just divide the probability by 1 minus that probability, and you're getting an odds value. So the example would be a horse. So if we have a horse that runs 100 races and wins 25 times, what would be the probability of that horse winning? So you would divide the total number of instances of that event occurring divided by the total number of experiments that we did, right? So it'd be 100. So 25 divided by 100, the probability of that horse winning a race would be 25%, right? On the other hand, of odds of that horse winning is going to be the total number of times that the horse won divided by 1 minus that, or basically the number of times the horse did not win. So in this case, it would be 25 divided by 75. So the horse won 25 times, did not win 75 times, so it would be 25 over 75, which would end up being 0.33. So in this case, the way you can convert that over, if you had the probability of that horse winning, you would just do that 0.25 or the 25% divided by 1 minus 25%, and that still gives you the same number, right? So basically 2 ways of kind of getting the same thing. That makes sense? So a little different the way they're calculated. Basically, we're just saying either what the probability of something occurring is, or what are the odds of an event happening. And you can see why the odds can be any kind of positive integer. So again, if the horse is winning many times, it could be 3 wins for every 1 loss, right? So it could be a positive value there. Okay, so when we're doing these case control studies, basically we're going to be comparing the odds of the event occurring between the patients who had the disease state versus ones that did not. And so these are going to be generating odds ratios. So in the case of those patients who are vaccinated, what we'd end up getting is that we had 10 patients vaccinated divided by 33 that were not. So we get odds of 0.3. Okay, so about a third of those patients end up odds of getting cholera. And then among the controls, you had basically 94 over 78, or you had an odds of 1.205. So if you were to compare those, which group of patients were more likely to end up getting cholera? Which one had a higher odds of getting cholera? People who are vaccinated or not vaccinated? Probably not vaccinated, right? Just because one, that kind of makes sense from that standpoint. But again, just looking at the numbers, you can see that you're much more likely for patients who were vaccinated, had lower odds of actually getting cholera occurring. So again, when you compare those proportions of odds together, you end up getting this case of a number of 0.3 divided by that 1.205, and you get 0.25. So the odds ratio of a patient who's vaccinated to get cholera is basically 25% of that of your patients who did not get vaccinated. Okay, so your odds are much lower of getting cholera if you are vaccinated versus if you're not. And so again, this would be another case where we're doing proportions. So if the 95% confidence interval encapsulate 1, then we know that the test is not significant. So in this case, it ranged between 0.12 and 0.54, meaning that the odds of patients who are vaccinated to get cholera could be anywhere 12% odds, or 0.54 or 54% the odds of getting cholera. So basically, what you can conclude from that is that vaccinated individuals are 25% as likely to get cholera as unvaccinated people, right? So we have an odds reduction here. And then if you wanted to turn it, and especially when you're talking about disease prevention, you can kind of flip that around to say basically the disease or the vaccine was 75% effective in preventing cholera from occurring, right? So you're realizing you see odds ratios versus relative risk, that they're a little bit different. Still trying to give you the same idea, but the values there are going to be different based on how they're actually calculated. And for case control studies, you're going to be using odds ratios because you're using prevalence of disease versus where you're going to use relative risk for incidence of disease as it goes forward in those prospective studies. Okay, so again, if we're interpreting these p-values, we're doing these odds ratios, so the small p-value, again, is going to tell us that it's very unlikely, just due to random sampling or random chance, that we would get results that are this extreme or more so. And so in this case, the p-value is 0.003. Again, you did not need to see the p-value because we already looked at the confidence interval, so it did not include 1, so you already knew those results were significant. But basically, there's a 0.3% chance that these results were just due to chance alone, so very, very small. And again, very frequently you're going to be using two-tailed p-values here. This allows for the chance that you could have more or less vaccine or more cases of cholera with the vaccine, right? Is there any idea, or can you guys think of a situation where a vaccine might actually cause disease? Yeah, so those live attenuated vaccines, especially if you have like immunocompromised patients, you can actually cause disease in those patients. So because in this case you weren't sure if the cholera vaccine would either prevent or cause disease, the results could go either way. We couldn't really anticipate which one would have the greater mean. We went ahead and used a two-tailed test, right? And those are going to be more robust, meaning it's going to be harder to make a type 1 error because of the fact that the values that we're going to have to achieve are going to have to be much more extreme versus with the one-tailed test. Right? Okay, so some of the challenges of case control studies you're going to run into. The advantage is one, it's going to be done relatively quickly. We'll have a relatively small sample size from previously recorded data, so this is really great for students to do, especially. My fellowship, my research was not necessarily case control, but basically we were using retrospective data because it's a lot easier to collect that than it is to do prospective data, especially when you're only on a 2-year fellowship. Some of the challenges, though, for one, if you're doing a true case control study, it's hard to pick the right controls because, again, you have to be looking at what type of confounders you think could be affecting your data, right? So if you want to make sure you have patients have similar age, or if they have similar disease severity or comorbid conditions, whatever happens to be, you have to be explicit about what you're controlling for there and how you pick your control patients. Again, the ideal is to control for any extenuating factors, but again, frequently you're not going to be able to capture everything. So there's always going to be that risk of bias there that could skew your data. And so again, the results are more likely true when the odds ratio is very large, when the results are repeated, or when the results make sense biologically. So always remember that. And it's a better way to help interpret that, to make sure that the results, even though it's a case control study, you can take a little bit more confidence in those results as they come out. Okay, so we'll continue on. My wife thought this was pretty similar to me. That was kind of funny. Can't say I took that as a compliment, but. Okay, so next we're going to be comparing two means. So basically this is going to be where our t-tests come in. So has anyone ever heard of a t-test before? Right, this is not where you're just measuring caffeine levels in your Liptons or anything like that. So we're going to talk about paired and unpaired t-test. There is also this idea of a single sample t-test. That's going to be an example where you're doing a sample mean and comparing it to a known population mean. Again, very frequently in the medical literature we don't know the population value, so instead what we do is we compare means together from different samples. And that's where we get those randomized trials where we're comparing usually a control group versus an experimental group. And this is where unpaired t-tests are going to come into play here. So unpaired t-test compares the means of two groups, assuming that the data is being sampled from a Gaussian population. And so again, this is assuming that we're using normally distributed data. So do you think the t-test is a parametric test or a non-parametric test? What do you guys think? Do you guys remember parametric and non-parametric? I know we talked about it. So parametric tests are going to be referring back to data that is normally distributed, or you're making the assumption that the data is normally distributed. So a parametric test will be used for that. A t-test is a parametric test. This is super important to remember. For non-parametric data that is not normally distributed, you're going to use non-parametric tests. Right? So we'll talk about those later on, but just know that t-tests are fairly but they are going to be an example of a parametric test. And we said that non-parametric tests are typically going to be more robust and they're more difficult to achieve significance because you're going to be trying to not make as many type 1 errors with those type of studies, right? Because again, we worry about outliers and things like that. So if you can get away with using a parametric test, you're more likely to achieve significance. Otherwise, you need to be using non-parametric tests for that non-normally distributed data.
Is that what you mean by like Gaussian population?
Exactly. Normally distributed, distributed population, Gaussian population, yeah, those are synonymous, absolutely. Okay, so we're going to be looking at some rats here. We're going to be looking at how well the neurotransmitter norepinephrine relaxes bladder muscle. I'm sure you guys probably have to go to the bathroom right now anyway, so this is appropriate. So essentially what the study that we're looking at here is they're going to be comparing the maximal relaxation of the bladder muscle with exposed to different concentrations of norepinephrine, and they're comparing whether or not old rats or young rats had differences in that relaxation, okay? And so they wanted to see if the differences between the two ages of rats were just due to chance alone, or if it was going to be actually due to some difference between those two groups, right? So if you look at the data here, this is going to be easier to look at when we're actually looking at a graphical representation of that, but this is just showing how much muscle relaxation occurred at different concentrations of the norepinephrine. So here you can see how the data is kind of laid out. We have the young rats having a higher degree of relaxation of the muscle versus older rats having generally a smaller degree. Which group do you think had more variation in the data or have a bigger standard deviation? Yeah, probably the old sample, right? You can see just how far distributed out that is. How could you test to see if that data was normally distributed? So how do you test to see if it's would be like a bell curve and normally distributed? There's normality tests we talk about, right? So you can do outlier tests, you can do normality tests to see if it is deviating significantly away from a Gaussian distribution or normal distribution. Just remember that there's ways to test for that. Because again, when we eyeball things, we tend to look for patterns that don't necessarily exist, right? So you always want to actually do the calculations to find out. So when they compared the two means, and again, those are those horizontal lines between the old and the young population, they had those mean values and they compared the two together. And so essentially what you get is an unpaired t-test. And an unpaired t-test, if you had to imagine what an unpaired versus a paired t-test is, what do you think the difference would be between that? So there's no actual relation between the two groups, right? So for an example, if I were to do, say, this experiment with the same rats, but I were to do some different treatment between the two, because it's the same rat, that would be considered to be, they're not individualized, they're the same rat, so that would be a paired example. If I were to do this to siblings, that would be another paired example. Because these two groups are independent, these are going to be independent groups, and you can use an unpaired t-test for that, right? Because those rats in the young group are not influencing the rats in the old group, and vice versa. Okay, so this is why we can use an unpaired t-test here. And if you look at it, the p-value came back at 0.003, so that would be significant or not significant? Do you consider that to be statistically significant? And then why do you think we used a one-tail or two-tailed test here? So you see here we use a two-tailed test. Is it because we had two different groups of rats? The two tails? Yeah. Sounds about right? Because imagine if you weren't sure which group would have the larger mean, right? So if I weren't sure if the old group would have the larger mean or the young group would have the larger mean, if I wasn't sure, then I would use a two-tailed test, right? Because I'd be less likely to make a type 1 error if I did not do that. So anyway, don't worry about the rest of this too much. We'll talk about some of this information later, but just focus on that top bracket there where we're looking at those p-values. So again, just a different way to compare the data here. Basically, same data we saw before on the left side there, and then here on the right side you can see that bar is basically the difference in the means. So again, they were basically just subtracted one mean from the other, and then you can see there I believe it's a standard deviation. Actually, I'm sorry, it's a 95% confidence interval there. So again, because we're subtracting means from one another, if the 95% confidence interval encapsulated 1 or 0, would that show us the results to be not significant? 0 or 1? I think 1? Because we're subtracting means from one another. We're not doing a ratio. 0, right? So anytime you're subtracting values from one another, subtracting means, 0 is going to be your non-significance point. If you're comparing them, if you're doing a proportion or a ratio, then it's going to be 1, right? That's why your absolute risk reduction, 0 is your point of non-significance. If you're doing relative risk, That was 1 at that point because then you're comparing the two. Okay, so interpreting the results from an unpaired t-test, when you do this, the mean maximum response for the old rats was 23.5, whatever units was lower than in the young rats, and that confidence interval ranged between 9.3 to 37.8. So we know the true mean difference there would be somewhere in that value 95% of the time. And again, because even though the confidence interval is wide, because we're using a relatively small number of samples, because it does not include 0, we can conclude that the old rats were statistically significantly different in their bladder relaxation response than the young rats. Okay, so in here we end up getting a two-tailed p-value that was 0.003. So again, we know that's going to be significant. Again, notice how you don't really need to see the p-value a lot of times if you can interpret the confidence intervals correctly. Okay, so it's a good point to remember. And here we can reject the null hypothesis in this example. Okay, any questions from the first section that you have? All right, so continuing on with our assumptions that we're using with unpaired t-tests. So when you're using this, you have to do the following assumptions. First one's going to be that this is a random or a representative sample of the population, right? So you're not trying to cherry pick patients based on anything that would kind of skew the data one way or the other, right? So it should be randomly sampled from your population based on your inclusion, exclusion criteria, whatever it happens to be. They need to be independent observations. So that's one of the key points here, is that the groups are completely independent. You don't have twins in the different groups. You don't have the same sample or the same subject being tested in one group and then the other. Whatever happens to be, they need to be completely separate from one another. Hopefully your data is accurate, so that's another assumption. And then because this is a parametric test, they need to be pulling from a population that has a Gaussian distribution or is normally distributed, right? So again, two populations, hopefully they have the same standard deviation, even if their means are distinct. That's kind of a one that you would like to see, but that's by using similar numbers of patients in each group or a similar number of samples. Hopefully your standard deviation should be roughly similar, right? Because a lot of that's based on your population size or your sample size when you're doing that, okay? So if you are looking at graphs where they're comparing, say, bar graphs and you're looking at error bars, it's important to understand what overlapping error bars can mean for you, okay? So we're going to be looking at a few different ones and what these situations can mean. So in this example where we're comparing the mean bladder relaxation or the muscle relaxation, and then looking at the standard deviation, right? So these bars are kind of going in both directions for the standard deviation. Now if these bars overlap, that's okay. It doesn't really mean anything for us. It just tells us the size of the variability in the data. So whether they're overlapping or not overlapping doesn't really matter too much to us as far as results from a t-test. Now if we were to look at standard error of the mean, and remember this is going to be telling us how closely this is going to be approximating the actual population mean in that group. And so when these do not overlap, you can be usually pretty sure or I'm sorry, if the standard error of the means do overlap, you can be pretty sure because those are so much smaller that the p-value is greater than 0.05. So at that point, you can kind of tell that your significance is not going to be met at that point. The standard error of the mean are close enough that they actually end up overlapping. Okay. And then looking at your 95% confidence interval, again, if these values do not overlap, then this is a good sign that your p-value is going to be less than 0.05. Okay, so if you're comparing two different means together, you've done a t-test and the confidence intervals do not overlap, then you can be assured that the p-value is going to be less than 0.05. Okay, so just to show you that in a table, what that means, you can kind of refer back to this. Very infrequently do I see things like standard error of the mean or standard deviation being shown on graphs in the medical literature, but very frequently the confidence intervals will be represented there. So be aware of that if they do not overlap, that you can safely assume that the p-value is less than 0.05. Okay. Okay, so let's say we were trying to compare two paired groups. So what do you think would be an example where you'd want to look at paired groups in an experiment? Anything of it all? Kind of mentioned one. So say I was looking at, say I did like twin studies, right? So say I took two twins and I was wanting to compare treatments, treatment versus control in those groups, right? Because we know they share genetics, there's a chance that there's some interplay there between the two that can maybe skew your data one way or the other, right? And so you're looking at something like a paired t-test can take care of that. Another example would be if you had the same subjects being treated with both, say, two different types of treatment. So say, for instance, I wanted to look at ratings in depression on patients. And so I were to take, one sample, this one person, and I were to give them the first drug, and then I look to see how depression scores change, and I give them a washout period, and then I give them another type of drug. And again, a washout period is a period where you allow all the drug and all the effect to kind of go away, and then you start the next set of treatment. Because that person has some interplay between the results there, there's some shared variability there. You use a paired t-test in order to help account for some of that, right? So this is where samples are not going to be independent of one another. So again, paired t-test for two matched or paired groups when the outcome is going to be continuous. And again, like we're looking at here, we can see that t-tests are going to be good for continuous data. When we're looking at something like the chi-square test, that's a lot better for data that's going to be nominal or ordinal. It's a lot better for that type of data. But t-tests are really good for continuous data. And again, this data, if they're paired or they share any kind of characteristics with one another, really need to be analyzed with this paired t-test. That's really going to be the only thing that accounts for that inter-subject variability that's going to be happening through that. Okay. So if I were to give you an example on a test, and I were to give you a study design where I was saying that we gave twins either placebo or we gave them an experimental drug and looked to see how their blood pressure changed, what type of test would you do to compare the mean changes in blood pressure? And so you would say paired t-test, absolutely, right? So there are other examples of where you can use a paired t-test, some things that might not be quite as intuitive. As we mentioned, a variable measure in each subject before and after an intervention. So you did kind of a pre and post because you're doing it in the same sample or the same patient. That would be an example of a paired t-test would be used. Again, if you subjects are recruited as pairs or matched for variables, one receives the intervention, one receives an alternative treatment. That would be another example. Twins or siblings, as we mentioned. If you were to have, say, a laboratory experiment that has a control and then a treated preparation, you're handling them in parallel. That's another good one. You can even have patients who are being treated on one side of the body with a drug and say a placebo on the other side, or the control on the other side. That would be another example of a paired t-test. And then if you're having the same subject having a measurement performed that's being done through two different routes. So say, for instance, I was doing manual auscultation, or I had an automated device that was measuring blood pressure at the same time. That would be another example using a paired t-test because it's on the same person, right? Okay, so this is kind of an odd example, but it came from the book. So this is an example where Darwin, he was actually looking at the growth of plants from seeds that were either being self-fertilized or ones that were being cross-fertilized. He wanted to see if there's any difference in the actual length of the growth of the plants, right, based on this type of fertilization method. And some of the ways he was able to control for some of these confounders, he made sure that the seeds were paired and control for changes in soil, temperature, and sunlight. So he kept them the same, those factors the same between the plants to see the differences in this fertilization method if it caused any changes in the actual length of the plants. So again, here's just the data that they're using when they're actually doing the paired t-test. Again, because we're using the same plants for either for multiple generations, that's why we're using a paired t-test, because again, they could be influencing themselves from one group to another. So essentially what they were looking at was the change in height. And again, if you were thinking about, if you're comparing heights between one group versus the other, would you use a one-tailed test or a two-tailed test? So if you're not sure which one's going to be bigger or smaller, you'd use a two-tailed test, right? So if you're not sure which direction it's going to go, then you would say, okay, let's use a two-tailed test. So I'm less likely to make that one of those type 1 errors. So here you can just see the differences in height between the cross and the self-fertilized. As you might imagine, what's the negative number here mean? It would mean the experimental group was shorter or less, shorter in length. If it's larger than 0, that would mean that would be an increase in length of the plant there. So again, when we did the paired t-test, basically came out to be 0.4 or 0.0497. You can see that the difference in means was 2.6 inches there. So you can see that the experimental group tended to do better, and that result would be significant, right? Because it was 0.0497, so it did achieve significance. And again, we used a two-tailed test there because we couldn't be sure necessarily which one would have the greater mean off the bat. You can also do tests to see how effective the pairing was. We're not going to get into that in this class, but just be aware that there are tests out there that can show how well your pairing actually was between the two samples. So looking at here, a paired t-test in regards to the confidence interval looks at the difference in measurements between the two matched subjects, or measurements they made before and after an experimental intervention, whatever it happens to be. But in this case, the sample data showed that the difference between the self and the cross-fertilized seeds was 2.62 inches, roughly 15%. And then that confidence interval ranged anywhere between 0.003 inches all the way up to 5.23 inches. And so notice here, because we're doing differences in means, so we're subtracting means from one another, that way we would use 0 as our point of significance, right? If I was doing ratios of growth, whatever happens to be, then that would be 1 as my point of significance. So again, even though the confidence interval is pretty wide, we know there's a lot of variability in the data. We can still say that yes, we achieved significance, and that by doing the cross-fertilized seeds, they tended to grow longer. Okay. As far as the p-value goes, we know that the null hypothesis would be that there would be no difference in growth between the two fertilization methods, but we were able to reject that because the p-value was 0.0497. And again, we already mentioned why why use a two-tailed test instead. Okay. So the next thing we'll look at is going to be correlation. So this is going to be looking at two variables and determining how much covariation they have, or if I change one variable, how does the other variable change in relation to that? So again, correlation, and what does correlation ever cause? Causation, right? So again, we'll talk about how we can determine how variables might be influencing one another and how you might be able to anticipate that in the next section, but right now we're just talking about correlation between two different variables. So for this example here, we're going to be looking at two continuous variables, right? And so you can quantify how well they correlate to one another by using this correlation coefficient, or R. So we're going to see R and R squared, and R itself is just this correlation coefficient, okay? So in the study here, in 93, basically they were hypothesizing that the lipid composition of cell membranes on skeletal muscle was going to be affecting the sensitivity of that muscle for insulin. So one of the things they were doing is they looked at 13 healthy men, and they were trying to determine their insulin sensitivity. So basically what they did was infuse insulin at a standard rate, and then they quantified how much glucose it took in order to maintain a stable glucose level. And that would give them an idea of what the actual insulin sensitivity was for those patients. And then at the same time, they would do a muscle biopsy to determine these polyunsaturated fatty acids that they had. And so their hypothesis here would be that as one of these values changes, the other one is going to change with it to some degree. We'll look at some of the ways that this can correlate to one another. But in this case, what would be my null hypothesis? Right, the changes in these polyunsaturated fatty acids has no correlation whatsoever with insulin. So we'll look at some of these graphs and how that kind of will show itself. So when we actually look at the data, and we'll show you that in a second, you see that both variables are pretty scattered. Again, you would like to see nice straight lines, but very frequently in the biological literature, you're not going to see that. But what they looked at, they were trying to find the differences in how much the data varied. And so when they looked at the mean insulin sensitivity, they saw that the standard deviation was pretty wide there. It had a very high coefficient of variation. So a lot of variation occurring there. And so they then decided to look at the fatty acid content. They actually saw much less variation with that data. So they said, okay, well, let's look at the variation, or let's look at the fatty acid composition, and then compare that to the insulin sensitivity to see how much this data actually compares to one another, how much they kind of they vary in the same direction. So this is called covariation or correlation. It'll be easier to see once you see the graphs. So when they looked at the patients, they're measuring that C20, 22 polyunsaturated fatty acids. You can see as content goes up, you could see changes in insulin sensitivity in those gentlemen that they measured. And so then you get data like this. And so what do you kind of notice about this data here?
Linear.
Yeah, it kind of looks like it's kind of shooting up at least in one direction. So on the x-axis, you're going to have your fatty acid content, and then on the y-axis, you have your insulin sensitivity there. And you can kind of notice like there tends to be a trend there, right? And so even though the data is scattered, we as human beings can see a pattern there. And so what the correlation is attempting to do is to tell us how much correlation is there. How much does when I increase fatty acid content, how much does that change with the insulin sensitivity, right? So there, in a lot of things, I can compare, lots of different continuous variables that might have no correlation together whatsoever, and you'll see no real trend there. As things covariate more, you're going to end up seeing more kind of clear trends. So I'll show you some graphs of what that looks like in just a second. So again, the direction and magnitude of this linear correlation can be quantified with that correlation coefficient. So that's that R value that we mentioned previously. Now these values can range anywhere between -1 and 1. And so that value is going to have different meanings based on whether it's negative, where it's actually at. So in this case, if the correlation coefficient is 0, this would mean that the two variables do not vary at all whatsoever. Again, I'll show you graphs in a minute that will explain this. If the R value is positive, that means that in general the values tend to increase or decrease together, right? So there's kind of a linear correlation there. Whereas I increase the fatty acid content, I would increase my insulin sensitivity. Okay. Now, if the R value is going to be negative, that means that the values are going to be inversely proportional. Right? So that means that if I were to see that line start to kind of go downwards, what you would see is that I increase the fatty acid content, you would actually see insulin sensitivity go down, right? So as one goes up, the other one goes down. If the R value is positive, both will go up and down together. So, and then if the values were either 1 or -1, you would basically see a complete correlation. You see a straight line, essentially. In the example we looked at, it was somewhere, in most of the times you're going to see it's between 0 and 1, or 0 and -1. But in this case, in the example, the R value was 0.77, right? So I'll show you that in just a second. I'll show you the line that best fits that. But here, if you're looking at correlation coefficients, you can imagine -1 to mean that the values are completely inversely proportional. So as one goes up, the other one's going to go down, right? Notice that's a straight line. You can see on the other end you have 1, whereas one goes up one value, the other one's going to go up exactly the same. So that would be a 1 R value of correlation. And then you have everything kind of in the middle. So 0 is like all scatter, meaning that there's no correlation between the two variables whatsoever. And then you kind of have everything in between. So for instance, you have -0.7, that's going to have a general downward swing, versus 0.8 will be kind of generally going in upwards direction. Notice as the values get closer and closer to the whole number, they get less and less scattered, right?
Will R end up being kind of like the slope of the best fit line?
We'll look at that in a little. That's when we start to do regression. So keep that in the back of your mind. We'll talk about that in probably the next section. But good question. Okay, so again, you can look at confidence intervals when you're determining these R values. And again, in this case, we see that the confidence interval, the 95% confidence interval of the coefficient, ranges anywhere between 0.38 and 0.93. Notice it's a little asymmetrical, depending on how the data is actually varying. But again, here, because it's not crossing 0, we would consider this to be statistically significant, right? Because 0 is our point where there's no correlation of the data whatsoever. Okay, and this is backed up by our p-value that showed it was 0.0021, so very unlikely that this variation of these two variables were due to chance alone. Okay, so it shows there's some sort of correlation there. And notice that it's a two-tailed test. Why do you think it's a two-tailed test? Right, because you don't know if the line's going to be positive or negative, so because of that, it could go either direction. Then you would want to go ahead and say, yes, we can use a two-tailed test. Now, for instance, if I were using something that I would only expect the values to go in one direction, so say I was comparing dose of lisinopril versus blood pressure, you would expect that to have a positive or negative coefficient value. Because as I increase my dose of antihypertensive, what does my blood pressure do? Should go down, right? So it's inversely proportional, right? So I would expect that to be a negative number. Probably would not be -1, but it would be somewhere in there. And essentially, I can look at that and tell me, that yes, as I increase the dose, there's some correlation with the blood pressure there, right? So in that way, I could use a one-tailed test, because I know exactly which way that I would not expect lisinopril to increase your blood pressure, so I could do a one-tailed test there. And so basically, the chances are very unlikely that this is due to chance alone, based on the confidence intervals that we have and the p-value that we're given. So again, correlation and causation do not always match up to one another, and so why do the two variables correlate so well? Well, we could say that maybe lipid content of the membranes does determine insulin sensitivity. Like that could have a direct corollary there. It could be that the insulin sensitivity of the membranes is somehow affecting lipid content. In a lot of cases, you're not necessarily sure what the actual correlation is, what the actual biological basis for it is, and very frequently you're not going to know the entire story, because in a lot of cases you could see that both variables could be influenced by something like hormones, right? Maybe the two don't, it's neither the chicken or the egg, it's something else that's causing both these values to vary together. You could look at lipid content, insulin sensitivity, and all of it just being part of one really complex network that you're just looking at two bits of the information, right? So this is where we're going to talk about more complicated regressions where you can factor in multiple variables here. But in this case, we're only looking at two variables. We're just looking at the correlation here. And very frequently, you need a lot more information, a lot more research to be able to determine anything definitive here. Okay, so again, correlation does not necessarily imply simple causality. Two variables can definitely be correlated without having any kind of direct causation. So for instance, if you're looking at the number of telephone calls per capita, or the number of telephones per capita, and look at increase at life expectancy, do you guys think there's any correlation there? Right, do you think one causes the other? Probably not, right? But you can still see a definite correlation there if you were to actually plot those out. So again, as with all statistical tests, when we're performing this, there are some assumptions that are going to exist here. So when you're making assumptions, when looking at correlation, some of the things you want to look at, one, this is a random sampling, just like we saw with our other ones. You want to be using paired samples, meaning that if you're measuring the lipid content from subject A, you should use the insulin sensitivity from subject A, right? You don't want to vary up your data and mix up who the subjects or what values are being paired with which subjects. The sampling should be from one population, right? So that way you're sure that the information should be same across the different patients. And they need to be independent observations. You're not measuring the same person twice or anything like that. The other thing is that the x values are not used to compute the y values, right? So you don't want the value of x to directly influence the value of y, because that's not really telling you anything at that point. It's just saying, because obviously if x was used to calculate y, as you increase x, y is going to go up as well, right? And then the x values are not going to be experimentally controlled. This is another thing where you're looking at just natural variation in the patients and how they're changing, and then how that the variable of correlation is changing along with them. You also want to assume that the data is normally distributed or Gaussian in nature, and that in this case, when we're looking just at strictly correlation, that the covariation is linear. We'll talk about nonlinear regression in the next section, but just know that in this case, we're just looking at linear correlation here. And obviously, no outliers. That kind of goes along with the Gaussian distribution as well. Okay, so then there's this other factor called R squared, and so this is what we're going to talk a little bit more about in the next section. But basically, this is the square of the correlation coefficient, and it's kind of an easier value to interpret, and allows us to kind of make some more inferences about the data that we're looking at. Now we know that R is always going to be between -1 and 1. But when we get the square value of that, that'll always be positive and should always be somewhere between 0 and 1. Okay, and then R squared is going to be the fraction of variance that's shared between the two variables. And I'll show you some examples of that when we get to the next section. So again, correlation, in here when it's used in its strict statistical meaning, it's just quantifying that association between two continuous variables. Could be interval or ratio variables, but they need to be continuous. And again, very frequently it's used used more generally. And then for that correlation or that coefficient of determination is just another term for R squared. So frequently you'll hear people just say the R squared value is such and such, and you can kind of take something away from that. Okay, so a few questions before we go into the next section, since I have some time. Can a t-test be computed from the mean, standard deviation, and sample size of each group? Or do I need all of the data? Think I need all the data? Actually, you don't need all of the data. Just by having the mean, the standard deviation, and the sample size, you can actually calculate, you can actually compare different means and use t-tests. That's kind of the nice thing about it, is that you don't actually need all that information. As long as the information is being reported accurately, then you can make the same test and come up with the same results the researchers did. Why is it called an unpaired t-test? Yeah, the samples are completely independent of one another, right? Otherwise, I need to use a paired t-test there. And then, does it matter whether the two groups have different numbers of observations? It's nice if they're close, right? Ideally, you'd want to have exactly the same value, but they can be pretty close. Obviously, as you get smaller sample sizes, you're going to run into issues where the variability in the data and standard deviation goes up. So you're more likely to end up making type 2 errors, right? So you're less likely to be able to reject that null hypothesis just based on sample size. So you run into some issues with that, but in general, as long as they're close, you're generally okay. Okay.
What n would you need for that to like apply? Like,
For
like your sample size.
mhm.
What number do you have to be above for it to be like okay with the observation?
It depends on what you're looking at, because again, if you remember when we talked about, the size of the effect can be a big factor into that. So if you're seeing a much greater effect, much greater change in blood pressure, change in LDL, whatever it happens to be, that's easier to find that statistical significance. If the values are very, very close together and there's a lot of variability in that data, it's easy for those confidence intervals to cross, right, and to not show significance. So if there's a small difference, you can use larger number of patients to get a smaller confidence interval, you're more likely to find that statistical significance. Now, if the values are way far off from each other, that's a lot easier, even if you have small number of patients. Usually they say 30 is kind of a good number of patients to have in each group to be able to make any kind of meaningful comparisons. But if you're dealing with a disease state that is very infrequent, or your population that you're dealing with is very small, whatever it happens to be, it can be difficult to reach those numbers. But good question. Okay, can I decide how the subjects are matched after collecting the data? No, why not? Yeah, I can skew my data. If I'm kind of cherry picking results and kind of matching people after the fact, you don't want to do that necessarily. So again, patients should be kind of matched. A lot of that stuff should be determined beforehand for the most part. Does it matter whether the two groups are sampled from populations that are not Gaussian? Kind of an odd question. As long as you can show that the data itself does not deviate meaningfully from a Gaussian distribution, usually you're okay. Because again, you don't have the whole population to really have all that information. You just make the assumption that you're pulling from a Gaussian distribution generally. Okay, does it matter which variable is called x and which one's called y in a correlation calculation? So could I put the insulin sensitivity on the x-axis and the lipid content on the y-axis? Yes, so for simple correlations, it doesn't really matter which one's which, right? When we start to get into regressions, you're going to see that you're more are saying, does X predict Y? In those cases, it is absolutely paramount that the X and the Y are defined. Here, if you're just doing a correlation, it really doesn't matter because, again, the variables are going to be varying how much ever they do regardless of which one's on X and Y. Can R value be negative? Yep, absolutely, right? We said if things are inversely proportional, you can see it have a negative value. How about R squared? Can that be negative? No, right, because that's just a square value, so it's always going to be positive between 0 and 1. If I double the number of points, can R, but R doesn't change, what happens to my confidence interval and p-value? So I increase my sample size. Yeah, it should get smaller. Or are you trying to pinch my head off? I can't tell. Which one? One of the two. Yep. So if I double the number of data points, I can lower my confidence interval and lower my p-value because again, those are getting more narrow as I get more patients. Okay. So any questions on that section? All right. I'm going to move over into the next one.